Yeah, great. Thanks a lot, Mark, for the invitation. Very happy to speak about this paper. Archive numbers on the bottom left. So this is a work that has been in the works, so to say, for quite some time, but I'm very happy that it's finally out. It's about momentum-dependent field redefinitions in asymptotic safety. If there are any questions at any point, please feel free to just interrupt me. So, okay. If you've seen any of my talks in the last few years, you know that I'm very interested in quantum gravity scattering amplitudes. So one of the long-term goals that I have is to compute such amplitudes in asymptotic safety to really finally get towards observables and also test some properties like unitarity and causality. So simplest example of scattering amplitudes are those that I've plotted here. So something like a 2-to-2 scattering. It's just the simplest process that you can imagine. Now, if you would want to compute such amplitudes, what do we need? What are the basic ingredients here? Well, for the left diagram, you certainly need the 2 and 3 point functions, so gamma 2 and gamma 3, which depend on either one momentum or 3 momenta. And then the vertex diagram on the right-hand side, that's just a 4-point function evaluated on shell. And that, of course, has 4 momentum arguments. So if you would want to compute this process, you need these ingredients. Okay, so there, of course, that's not an easy task. So you certainly need full momentum dependence. Otherwise, what are you really talking about? You need Lorentzian signature because scattering is intrinsically Lorentzian. For example, if you want to go on shell and have something like p squared is 0 for a massless particle, in Euclidean signature, this means that the momentum is just 0. Whereas, of course, in Lorentzian signature, this doesn't mean, this is not the case. Now that's quite a lot. So the problem is that this is really difficult. It's a lot to compute, and any help that one can find to make this simpler is, of course, appreciated. And the tool that I want to advertise, or the idea that I want to advertise here, is that you can get major simplifications if you use what is nowadays known as the minimal essential scheme. Now I'll explain a little bit in more detail what this really means. But kind of the cartoon version is, so this figure you may know, Pippi Longstrump, Swedish TV show for children. And in German, she has a very nice song, so the title melody, and basically translated, it says, "I make the world as it suits me best." So this is what I'm doing here. I'm performing field redefinitions to change the effective action into a form that I really like. So this is kind of the nutshell of my talk, if you want, or the basic idea, basic premise. Now, this will fill the next, I guess, 45 minutes. So the first half of my talk will be about field redefinitions in quantum gravity, and we'll ramble a little bit about that. There's certainly some aspects that we have to discuss there. One has to be very careful in what one allows and what is not allowed. And the second part is going more into the actual computation, which is exactly implementing this and what you would think as trivializing the propagator in asymptotic safety. So split up in several parts. First is the setup. So how do you Pippi Longstrump the effective action? And I will give you a very short glimpse on the actual derivation of the flow equations for the setup, which fills the 23 pages of the appendix, but is completely analytical. And then I will discuss both analytical and numerical results. So let me start with the ramble about field redefinitions. So going back, in a sense, to the scattering event, and for simplicity, let's just discuss scalar scattering, right? So you have a scalar field phi, which is maybe Z2 symmetric, and you want to investigate how two of these scalars scatter into themselves. and you allow for both self-interactions of 5⁴, or momentum-dependent generalizations thereof, and the interaction with gravity indicated by this H propagator here. And of course, I should say that I will use the effective action in all the discussions today. So all these vertices and propagators are fully effective quantum vertices. Now, some time ago, we studied exactly the scattering in these two papers, and we wrote down the effective action that you need to describe the scattering in a flat background. And this has these three lines. So the first line of the effective action parameterizes the graviton propagator. You see that you need these form factors, FRR and FSS. They give you the non-trivial momentum dependence of the graviton propagator here. The second line parameterizes the 3-point vertices, essentially, and if you want the scalar field propagator in terms of yet more form factors. So now you have interaction form factors FR5 with 3 arguments and FS5 3 arguments. Should maybe say that S is the traceless Ricci tensor here. And last but not least, you have another form factor F5555, which gives you this contact term, and that depends on 6 momentum arguments in total. So it's 6 scalar momentum arguments. So this whole beast is the thing that you need to describe this scattering. If you give me all these form factors, I can give you the amplitude, or you can look it up yourself in these papers, and you can just extract the amplitude from these form factors. Now you can see just from looking at this action that there's a lot of things to compute. So maybe we can simplify this. And the way to go, I already mentioned it, is via field redefinitions. So observables like the scattering amplitude that I've shown you cannot depend on our technical choices. And one of such technical choice is, of course, how we parameterize the field, the fundamental field. So we can redefine fields in the path integral. Of course, there are some conditions that apply. I will list some, certainly not a complete set, but some very important ones. So what you do not want to do with field redefinitions is to remove or add degrees of freedom. So if you think of, for example, a massless scalar field, if you would do a field redefinition like this, so phi goes to 1 over square root of the kinetic term times phi, you're just mapping a free scalar field into just phi squared. And of course, now you've removed the scalar degree of freedom out of your theory. And that's not good, because now you've changed the physics. So certainly field redefinitions like this, you should take very carefully into account, or just disallow them. The second point that I want to make is that non-local redefinitions can also be dangerous. And let me give you a little bit of an example here. For that, very easy example is scalar field theory, phi⁴ theory. So I've written down an action here. You have just a kinetic term and a phi⁴ term. And now you introduce a new scalar field, capital Phi, by this rather non-local prescription. So you see there's, first of all, a square root of this operator, and then there's a 1 over box acting on everything that follows on the right. If you want to make sense out of this, think of a perturbative series in lambda, and then you can define it order by order. And then if you plug in this field into, or like if you do this transformation, you see that you map the original action into just a free field theory for the capital field phi. So somehow the scattering of this capital field phi seems to be trivial, whereas certainly the scattering of the standard phi is non-trivial because you have an interaction. So something happened here. And you have to be, once again, very careful if you allow for non-local field redefinitions in such a way. Why is this relevant for gravity? Many years ago, in 2009, there was this paper by Krasnov who suggested a non-local field redefinition to remove the Gaussian-Naughty term in gravity, so the y cubed term. And it kind of mimics this structure. You have 1 over box terms in this field redefinition to eventually get rid of this C cube term. So from my perspective, you have to be really careful if you want to do this, and certainly you have to kind of understand where the interaction is going. So coming back, as a short summary, non-local field redefinitions can be dangerous, and you have to be very careful in what you're doing. Now, with these conditions, you can there's still, of course, a set of admissible field redefinitions, and you still have some choice there. And then different choices give simply rise to different schemes. And if you think of these 2 diagrams that I've shown you for this amplitude before, different choices of field redefinitions simply move the momentum dependence from one diagram to another. But the overall amplitude should, of course, stay the same if all the conditions that are listed here, and maybe some more, are satisfied. Now let me discuss the minimal essential scheme. That's one particular scheme to where you use field redefinitions to set everything to 0 that you can set to 0. That's kind of the basic idea here. So you want to simplify your life and throw out as much irrelevant information out of your system as possible. To do so, of course, since by the conditions that I mentioned, you do not want to add or subtract degrees of freedom, for example, you have to make some assumptions on the spectrum of the theory if you want to implement exactly this scheme. Namely, you have to fix the spectrum, so how many degrees of freedom are propagating. For gravity, you could say, well, there's something like a GR universality class, if you want to call it like that, where the propagator is specified by only having a mass as pole, so exactly the property of GR. You could also define a different scheme or class of theories, which you might call stellar, where the propagator then has the spectrum of stellar gravity, so an additional massive spin 2 pole. And clearly, so these 2 classes of theories, you cannot map one into the other because they have different physical properties. So field redefinitions between the 2 should not be allowed. But on the other hand, once again, to emphasize that if you want to investigate one specific class, let's say GR, you have to kind of put that into your assumptions. And then the nice thing is that in a theory with a given spectrum, let's say GR, you can put the propagator into a tree-level form by field redefinition. I will be very explicit in how to do that. So in this class, GR, in some expansion, if you want, you can map the metric into this redefined metric. So you introduce some form factor AR box acting on R and AS box acting on S. And if you choose these 2 functions AR and AS appropriately, you can remove your FRR and FSS out of the action. But of course, you will get higher derivative terms, but at least the propagator will be simplified by this. And the choice is written down in these 2 equations. You might be worried at first glance that these are actually non-local because you see these 1 over box terms. But actually, if you look more carefully, these 2 expressions are infrared finite. Because if you look at the brackets and expand them for small box, you see that this is something like 1 minus a third. The 1 over square root is roughly 1 plus corrections, and then minus 2/3 times 1. So this gives the bracket a 0 at box equals 0, and then you will get a linear term, and so this is finite. Same thing for the AS. The square root is approximately 1 for a small box, so 1 minus 1 is 0, everything is finite. Second thing to note here is kind of by assumption of being in this class of GR, these square roots in the denominators are well behaved. They are not singular anywhere in the complex plane, because these are just the combinations that would appear in your propagator if you start with the original action. And by assumption that you only have the standard pole, namely the pole of GR at p squared is 0, these terms are all finite. So 1 plus box FSS box is finite, and also this combination of FRR and FSS is finite and positive. Okay. Now you can play this game at higher and higher orders. So you can add more terms to this. And what you can find is that you can remove almost all momentum dependence from 3-point functions, except for some local terms. So one thing that you cannot remove is the Gauss-Narnotti term, because it doesn't vanish on shell. It's kind of the underlying reason. But any form factor that would add on Gauss-Narnotti can be removed and shifted into a 4-point function. Another example of a non-vanishing 3-point function would be if you have, for example, a photon, then you can form a combination of 1 Weyl tensor and 2 field strength tensors that also cannot be removed by such a field redefinition. So kind of the bottom line is propagators can be simplified enormously, 3-point functions as well. So all the momentum dependent, non-trivial momentum dependence can be shifted into the 4-point function. And even there, you can remove most of the momentum dependence. So to make that more precise, coming back to this example of the scalar scattering, I've written down yet again the original action. And now I assume that we are in the GR class. So I only have a massless pole in the graviton propagator, and I have maybe a standard a massive scalar field. And I do a field redefinition. And if I do that, I can map this big theory into the small theory in the last line to describe the same scattering. Now, of course, if you look at other scattering events of maybe 6 scalars or also graviton, external legs, I need more terms to describe that, but these terms are also not complete in the original action. But for the sake of this 2 phi to 2 phi, you can describe this whole scattering in terms of basically just a modified phi to the 4 interaction. And the relation between the two formulations is simply a field redefinition. So you see that you really can simplify or basically trivialize the left diagram here. And all the non-trivial information is then in the contact term. Yeah, so that's basically all the magic happens in this right diagram. So what's the path forward to compute scattering amplitudes in asymptotic safety? Well, we might want to use this minimal essential scheme to simplify our computations, because remember that in the flow equation, the thing that drives the flow is the propagator. And that's the thing that's in the denominator. And denominators are always harder to treat than numerators. So if we can find a way to simplify maximally the propagator, we've gained a lot. And this is the way to do it. So the first step towards scattering amplitudes now would be to implement these running field redefinitions to put the propagator in tree-level form at every RG step. And that's kind of the idea of this paper. To remind you how the flow equation looks like in this context, so there's some extra terms. This originally goes back to the very general flow equation by Jan, and then has been kind of supplemented with this minimal essential scheme by these 3 gentlemen, just by now 3 years ago. So you certainly know the first term on the left-hand side and the first term on the right-hand side. So the flow of gamma k is related to the trace of the propagator g times k dk rk. And then there are 2 additional terms in this modified flow equation when you allow for running field redefinitions. On the left-hand side, you have this psi k. Psi k is essentially the flow of the field redefinition. So something like the expectation value of dt of the field, of the running field. You contract it with the equations of motion. And on the right-hand side, there's simply an insertion of this running field redefinition, and well, it's field derivative. So this is kind of the basic structure. You also see that this essential scheme is closely tied to an on-shell condition, because if you go on shell, gamma 1 is 0, so you would get the flow of the stuff that survives on shell, which we would call the essential couplings, by simply going on shell in the flow equation, and then you don't see the field redefinition on the left-hand side. You still get a contribution on the right-hand side from the fluctuation or from the variation of the field redefinition, but it's simply the price that you still have to pay. So that it's not trivial in the end. You still get non-trivial flow information for these field redefinitions. Okay, so a lot of rambling. Maybe this is a good point to stop and ask if there's any question about that part. If not, I can continue with the setup that I'm looking at.
Hi, Benjamin. I do have a question. So in the end,
Yes.
if you want to compute the full 4-point function, does that so your simplifications in the scheme are at the lower orders, but do you add complexity then to the fourth order because you push all of the information there, or is it still tractable?
It's still tractable. So maybe to make this point a bit clearer. So in the end, there's no free lunch, right? So
yeah,
somewhere the complexity is hidden, of course, but you shift it, at least that's my perspective, you shift it into a part where it hurts less. Because as I said, like the propagator is kind of the thing that hurts most, because if you have a very intricate denominator structure, integration over that is always a little bit tricky. And if you can get it into just a p-squared form, that always helps for threshold integrals.
Sure. Okay.
At the very end, if you want to evaluate this amplitude, you anyway go on shell, and basically what survives going from this general action to this minimum essential scheme action is basically the same, because so you set kind of all the pi squareds to m squared, and what survives from these 6 arguments, for example, from this original 4-point function, are these 2 arguments. That's s and t, if you think of Mandelstam variables. So in a sense, you kick out everything that is off shell in your scheme. You still have to compute stuff. I will show that in some more detail. So it's not that you can completely remove it and only compute with these. That's why you have this psi k everywhere. But at least for the kind of the relevant part is much simplified. And you can see that from the structure of the flow equation, psi only appears in numerators and linearly, so that you get a better technical handle on it than having these things in the propagator.
That makes sense. Thanks.
No worries. Any more questions? Otherwise, I can continue and talk about what precisely I have investigated, having this whole setup, or this whole kind of philosophy in mind. So the ansatz that I'm looking at is very simplistic. I basically look at the gravitational part of this action. So maybe going back very briefly in the bottom line, the only thing that I add is a cosmological constant, but otherwise, and the topological term, but otherwise it's basically this lower line without the scalar field. So I'm concentrating on the propagator of the graviton for now. because you have to start somewhere. So basically, this is the ansatz. You have Newton's coupling, you have the cosmological constant, and you have a topological coupling, which plays not really an important role here. But you can add it, so I added it at this order. This psi k, how does it look like? Well, it kind of looks like the field redefinition that I've shown you before. You have these gamma functions now, which are related to the flow of this field redefinition. So you have a gamma g, which multiplies the metric. You have a form factor gamma r, and then the form factor gamma s. I supplement this with a harmonic gauge fixing to simplify everything as best as I can, kind of in the same philosophy as using a minimal essential scheme. This delta 2 is a very particular operator. It has some endomorphism, which is traceless. And so this is the operator that you get in the 2-point function if you take this action together with harmonic gauge. That you get, so and then this delta 2 is basically the TT part of this gamma 2. And there's nothing else left. Sorry, that's not quite true. It's true if you go on shell. So whatever is not of this form comes kind of with a lambda. Okay, why is this nice? Well, if you use harmonic gauge with this action and this operator and regularize this operator, your propagator is extremely simple. It has a traceless part and a trace part, and both of them have a propagator function, g, which basically looks the same, just that once you have this operator delta 2, and once you have just a standard Laplacian. So, and this is kind of the magic now that in this minimal essential scheme, you only have a p-squared propagator, basically. And the information on the field on the momentum-dependent field redefinition is stored in this gamma r and this gamma s. Okay, so very simple propagator, very simple regulator, very nice. So where's the hard part? So the no free lunch part, right? So let's look back at the flow equation. So certainly the left-hand side is completely easy to evaluate. The KdK is very straightforward. Computing the equations of motion is very straightforward, and then contracting with this ansatz for psi k is very straightforward. So the hard part must be in this RG kernel insertion on the right-hand side. And that's indeed the case. So this is exactly where the no free lunch part is. The first part is just like 5 minutes because the propagator is so easy, the regulator is so easy. But then the second piece, that takes many, many months and the 23 pages of computation. And I want to illustrate that a little bit, that you get at least a taste of what is so difficult about it. So with this RG kernel insertion, so by that I mean exactly this red term, once again, many contributions are kind of straightforward. There's some non-trivial contributions where you have the perturbation of the form factors. So maybe let me go back to illustrate that again. You have these form factors, gamma r and gamma s, which depend on the Laplacian. And to compute this term in the red box, you have to take a variation of that. And this, of course, introduces some kind of non-triviality into the whole computation. But there's a formula for that. So if you want to compute a variation of a function of an operator, you basically use the inverse Laplace transform, this L inverse, and then you basically set it and can make it tractable. The really hard part is that there's one contribution where you need the off-diagonal non-local heat kernel coefficient of this form. So 2 derivatives and a fully non-local heat kernel, 2 second order and curvature. So this, to my knowledge, was not known in the literature, so I had to compute it. And once again, to give you an idea how long this is kind of one part of the formula. So maybe let's focus on the first line here. on the left-hand side, this is what the heat kernel coefficient is that we need. And you can split it into two contributions. One is just the diagonal heat kernel. And then there's this kind of non-trivial bit that is listed in this A46. So you don't have to look into the details. It's just to give you an idea of what the complexity is of such a computation. Yeah. So this is kind of where you spend a lot of time in such a computation. Okay, that was kind of the more technical part. Let me discuss some results. So of course, you first want to make sure that you've not made any mistakes in these 23 pages of computation. So you make some sanity checks. The first sanity check would be something like the run loop running that you get from GR. And how you see it in this minimal essential scheme is in the gamma R and gamma S at zero argument. So gamma R is kind of related to the R squared running, and gamma S is related to the S squared running at small g. And indeed, as otherwise I wouldn't present it, of course I get the right numbers here. In the same way, perturbatively, you get the right running for the topological term. So maybe you know this 53 over 45 as a kind of thing that should come out of a one loop computation. So that's good. It has the right perturbative limit. Then we can study a little bit the asymptotic behavior for large momentum of these gamma functions. And you find that they actually decay like 1 over p squared with some number that in principle you can compute, but not quite, because kind of structurally what you find for these gamma R and gamma S are integral equations that involve the gammas themselves within and without, inside and outside of integrals. So you cannot really compute these CR infinity and CS infinity in closed form, but you can compute them order by order, for example, in decoupling G. And here I've written down the leading term for both of these. So there's some kind of threshold integral that is just regulator dependent. But you can see that both of these constants are negative. Okay, then another thing that you can investigate is whether this whole setup fulfills momentum locality. Maybe as a reminder, momentum locality is related to the large momentum behavior of the flow of a correlation function in terms of the correlation function itself, and is kind of related to a well-defined block spinning procedure. The kind of momentum locality. So this is some relatively old by now concept that has been found in fluctuation computations. So for fluctuation computation, you get that such a limit of the two-point function is actually 0. But here, as a background computation, I find that I do not have momentum locality, neither in the spin 2 channel, nor in the spin 0 channel. So at this point, I'm not really sure what that means, to be honest. It could just be another indicator that you actually simply need a fluctuation computation to get this property. Onto the numerical results. So fixed point structure. What do I find? There's simply a single unique fixed point. And I want to compare this fixed point first if I do not take into account the form factor gamma functions, and then in the full system. So if you do not take into account these form factors, that's kind of the cheapest thing that you can do. It's HN Hilbert like. These are the values that you get. So you get a critical exponent of 2.338 for an exponential regulator. Now include these form factor gamma functions, so gamma R and gamma S. What changes? Well, basically nothing. The change in the critical exponent is less than 1%. So as a kind of bottom line here, one finds that these these momentum-dependent field redefinitions play numerically absolutely no role. That is really interesting because I mean, this is basically the momentum dependence of the propagator, right? So it seems that this is somewhat unimportant. Okay, let me show you some nice plots to maybe illustrate things a bit clearer. What I've plotted here is the beta function of Newton's coupling, and then this gamma function, gamma g, which was in front of the metric. And where you see that the beta function is kind of relatively flat curve and has a fixed point here at g roughly 0.28, I guess. And the gamma function basically increases towards negative direction roughly linearly. Okay, now you can look at the difference between an ancient Hilbert truncation and the truncation with the form factors for both these quantities, and you see that's at the level of sub%, as you would expect from seeing that the critic exponent doesn't change really. So also here you can explicitly see that the change is completely negligible. How do these gamma functions look like? It's plotted here. So for relatively small momentum arguments, you see gamma r, well, negative and relatively flat. In gamma s, there's a little bit more variation, it goes from positive values to negative values. But then if you look at a more global perspective, so here I've used compactified coordinates, you see that both of them eventually go to zero at infinite momentum. Okay, I also have some nice 3D plots. So gamma r and gamma s as function of momenta squared and g. And you see that they basically very slowly turn on as you turn on g. Okay. So what are the properties of this fixed point? I think you can say that this is really the standard Reuter fixed point because it's basically numerically the same. There's really the same signature. And from my perspective, this is a strong indication, or yet one more indication, that this fixed point is actually in this class of GR, that it does not have additional degrees of freedom. There's of course a connection to the nice works by Alessia and Christoph, who explained this mechanism where in a standard scheme you add in a derivative expansion more and more poles, and then in the limit where you take all fiducial poles into account, they kind of decouple and leave you with the standard pole of the full theory. And you can kind of avoid to having to add all these infinitely many poles order by order by implementing this minimal essential scheme and still having the full momentum dependence working at the back. And the second kind of takeaway point here is that really these running momentum dependent field redefinitions, at least at this order, are quantitatively completely unimportant. And that's a very important observation, but completely in line with a similar observation in this paper that I had together also very recently with more colleagues. And we will actually have a talk by Yannick in, I think, 2 weeks on that in the Asymptotic Safety seminar. And Yannick will talk about this paper where we see essentially the same, that the gamma functions there in such a derivative expansion also are not really that important, except the gamma g, but I expect that Yannick will talk a bit more about this than I will. But certainly the gamma r and gamma s quantitatively are completely unimportant, at least as far as we can say from this study. Good. To summarize, kind of quoting myself, I guess that quote is from me, asymptotic safety is really maximally boring. You really only basically have physically a scaling regime in the infrared and another scaling regime in the UV and some crossover and nothing more. And kind of this finding kind of plays into this this idea. I think that the fixed point that we've found and that we continue to find, the Reuter fixed point really seems to lie in this class of GR. So more and more we have indication that we really only have a single pole, a single massless pole for the graviton. And then maybe as a last point is that this minimal essential scheme is unreasonably stable. So somehow together with this other paper, so in 2 weeks, you will also see that it seems kind of to implement this idea of asymptotic safety being maximally boring at a very efficient level. And then maybe as a homework problem for you, of course, just compute a 3- and 4-point function in this frame. But yeah, that's of course in the future an important step to see what happens there and to finally get to amplitudes. And with that, I'm done, and I would like to thank you for your attention.
Yeah, thank you very much, Benjamin, for the nice talk. And